In this video, we're going to look at the chain rule for two or more independent variables. We're going to use tree diagrams to aid us in understanding the chain rules for several independent and intermediate variables. And then we're going to perform implicit differentiation on functions of two or more variables. So here's a couple of warm-ups. We're going to do the derivative. Now these are in one variable, so Calc 1 type stuff. So we're going to do the derivative f prime of x. Or if you prefer, dy dx is equal to. By the chain rule, I bring the -1 down up front, and then we have the natural log of 3x to the fourth raised to the -2. That takes care of the outermost function. And then I'm going to multiply by the derivative of the inner function, which is the natural log. So that's going to be 1 over the 3x to the fourth, because that's my u, 1 over u. And then it gets multiplied by the derivative of u, which would be 12x squared. And then, of course, we can clean this up algebraically, and so we end up with negative, 12, and that's 4, and then that should be cubed, by the way, not squared. Make that into cubed. And by the way, my cat's helping me, so just so you know, I have a lot of cat help right now, which is really awesome. Or not, depends on how you look at it. That should be x. Okay. So what I end up with is a negative, and then 1 over, I have x, and then the natural log of 3x to the fourth, and then the quantity squared. Let's go ahead and do the derivative of tangent. So that's my most outer function is actually the cubed. So g prime of x is going to be 3 the tangent squared of the cosine inverse of the square root of 3 minus 2x squared. Whew. Now I'm going to do the derivative of the tangent. So I'm going to multiply by the secant squared of the cosine inverse of the square root of 3 minus 2x squared. Now we're going to go ahead and do the derivative of the cosine inverse. So that's going to be 1 over, and the cosine inverse should be a negative, the square root of 1 minus the square root of 3 minus 2x squared, the quantity squared. And then I need to do the derivative of the square root part, so that's going to be 1/2, and then 3 minus 2x squared raised to the -1/2. And then I'm finally ready to go the most inside function, so this is going to be multiplied by a -2. That should be 2 times 2 is 4. Bring that power down using the power rule, -4x. Okay. So that is one super long derivative. The next one is going to be implicit differentiation, but it's not as long as the last one. So let's go ahead and do implicit, because I can't solve for y by itself. So I'm going to do the implicit differentiation, which gives me 2x plus, and then I have to use the product rule here. So it'll be 1 times y plus x times 1 times dy dx. And then I'm going to do the derivative of y, so it's 2y dy dx is equal to 0. Since I'm trying to find dy dx, I need to move any of the terms that doesn't have a dy dx as part of it to the other side of the equal sign. So on the left side, I will leave it with x plus 2y, factoring out a dy dx is equal to. On the other side, I'm going to end up with a -2x and minus y. I'm going to divide both sides by the x plus 2y. And so my final answer, dy dx, is equal to -2x minus y over x plus 2y. Bam. So, it's not too bad. So let's take a look at the chain rule for one independent variable. Now suppose we've got x is equal to a function in terms of t, and y is a function in terms of t. Then z, which is f of xy, is going to be the same thing as z is equal to f of x of t and y of t. Then the partial derivative, the dz dt, is going to be the partial derivative of z with respect to x and the x respect to t. And of course, the partial derivative of z with respect to y, and then y with respect to t. Okay. So it's not uncommon to use a tree diagram to kind of keep us on track, because there's a lot going on with these. So here is a tree diagram for the case where I have dz or dz dt. So here's my function f of xy, and then going around this branch, the derivative of z, the partial derivative with respect to x, is the partial derivative of x with respect to t, multiplied together, this branch times this branch. And then going down this branch, I have the partial derivative of z with respect to y, and then I have dy dt, and you can go down along the branch, and you multiply along the branch to get the end. And then, of course, you add the end branches together, which is why we end up with this. Now let's look at what happens when I have my function z in terms of x and y, but x and y are in terms of other functions. So x is really a function of g, which is a function of u and v. The same thing with y is a function of u and v. And we get the partial derivative of z with respect to u is equal to this, and the partial derivative of z with respect to v is equal to this. So here is the decision tree when I have z, which is in terms of x and y, which in terms is in terms of u and v. And of course, as we go down the branch, we multiply this and we get this. Multiply this and this, we get this. And we multiply this and this. And so I have the partial derivative of z with respect to u will end up being this branch. Or actually, it'll be this branch and this branch. It would be this branch and this branch. And then the partial derivative with z with respect to v would be this branch and this branch. And again, I multiply down along the branches, or I multiply along the branches that way. And then I add the appropriate branches. So then let's generalize this. Now, this is why sometimes the tree diagrams are helpful, is so that you can kind of keep track of what's going on. Now, suppose you have this w. So you have this function w, which is all of these x sub 1s to x sub n. And each one of the x's are in terms of these t's. Then if I have a case where I've got dw with respect to t, I have all of these additions, and I would follow that branch. And so I'd have something that looks like this. If I'm doing it with respect to t, then I would go down this and this pathway, and I would have that, but then I'd also have to do it with the y, and I'd have this one, and I'd have to do it with respect to w and or z, and I'd also have that one. So of course I have with respect to u, and then with got wild and crazy there, that should be v. And so now also with respect to v. Let's go through an example. So calculate the dz dt for each of the following functions. So I'm going to need the partial derivative. So the partial derivative of partial derivative with respect to x, the partial derivative of f with respect to x is just going to be 2x. And that gets multiplied by the derivative of x with respect to t. So this is just going to be 1. So if I was going down my branch, I'd be going down the x side. So this would be the dx dt, which is equal to 1, and my partial derivative df of dx, which is equal to 2x. So down this side it'd be 1 multiplied by 2x. And then I'd be going down this other side here. So I'd do the partial derivative of f with respect to y, which is 2y. And then dy dt, this is going to be 2t. So down this side I have the df dy, which is equal to 2y. And along this branch I have the derivative of y with respect to t, which is equal to 2t. And so I end up with this branch being 2y multiplied by 2t. So dz dt, so dz, not partials, these are full derivatives, the derivative dz, of course my cat's biting on the edge here, that's pretty awesome, dz dt is going to be equal to 2x and then plus 4y t. And then to get everything in the same variable, since we know that x is t and y is t squared, this would be equal to 2t plus 4 multiplied by t squared multiplied by t, which gives me 2t plus 4t cubed. And that is my final answer. Okay, let's take a look at this one. And once again, I'm going to have my two branches. My first branch here is going to be the partial derivative of x with respect, partial derivative, of z with respect to x, partial derivative of z with respect to x. And then I'm going to have dx and dt. So my dz dt, so that's going to be 1 over the x plus y multiplied by 1. That is my dz dt. That gets multiplied by my dx dt. Well, my dx dt is e to the t all day long. Going along my other branch, I have my partial derivative of z with respect to y. And that is going to be 1 over x plus y multiplied by 1. And then I want to have the dy dt, which is going to just be e to the t. So if I want to find dz dt, this is going to be equal to 1 over x plus y e to the t plus 1 over x plus y e to the t. But bringing everything in terms of e to the t, I'm going to have 1 over, and then I have both x and y are equal to e to the t, so I have 2 e to the t multiplied by e to the t, plus 1 over 2e to the t multiplied by e to the t. And we can see our e to the t's cancel and giving us just 1/2 plus 1/2, so my answer is 1. Now on this one, we have 3 variables, so I would need 3 branches. I'd have first my x branch, and then I'd have my y branch, and then I would have my z branch. So going down my partial derivative, so my partial derivative of x with respect to, partial derivative of z with respect to x is just going to be 2x. And then it's going to be multiplied by, x is the cosine of t, so that derivative is going to be negative sine of t. So that is, actually I should note this as, and then dx dt. So this is equal to, one more time, 2x, and then it's going to be multiplied by negative sine of t. Going down the y branch, so the dy, partial derivative of, I keep doing that, the partial derivative of z with respect to y, and then I multiply that by dy and dt. So the partial derivative with respect to y is just going to be 2y. The derivative of sine is cosine of t. Going down my last branch, the partial derivative of z, oh, these all should be w's. Darn it. Okay. These should be w's. This is what happens when I'm not paying close attention. This is the w, this is w, and of course, and this is w, and then partial derivative of z. And then this gets multiplied by the dz dt. So the partial derivative of w with respect to z is 2z. And then the derivative of e to the t is e to the t all day long. So of course, these then, with the replacements, so what does this become? This becomes 2. And of course, my x was the cosine of t multiplied by the negative sine of t. And then I have my next one here. So this is equal to 2, and then y is the sine of t replacement multiplied by the cosine of t. And this is going to be 2 e to the t multiplied by e to the t. So all these get added together. 2 the cosine of t sine of t, and that's a negative. And then plus 2, the cosine of t, the sine of t, and then plus 2e to the 2t, and we can see that these cancel themselves out, and my final answer is 2e to the 2t. That is my final answer. Now it's also asking me to find it directly and then find it using the chain rule. Well, I did it with the chain rule first because I was already there. So let's do the direct substitution. Let me erase all of this and do the direct substitution. So with the direct substitution, that means I'm going to substitute right out of the gate. So my w is going to be, and it'll end up just being w of x of t, y of t, and z of t is equal to, wherever I see x, I replace with a cosine of t. So that's cosine of t squared. And then plus the sine of t squared plus e to the t squared as well. Using our usual chain rule, this is going to be 2 cosine of t, dropping a power, multiplied by the negative sine of t. So negative sine of t. Erase that. Negative sine of t. Negative sine of t. And then plus 2, dropping a power, the sine of t, multiplied by the cosine of t. And then, of course, let me give myself some more room. That is going to be e to the 2t. So that is just going to be 2e to the 2t. And as before, these two cancel themselves out, and I'm still left with 2e to the 2t. So you're asking me, why do I learn that chain rule like that? It's kind of a hassle. Well, we'll get there, and I'll show you why. It's kind of like helps us with the implicit differentiation, which is where we are now. If we think about the fact that the function, when we're in Calc 1, we had to find dy dx like we just did, which can be a little messy. Now, if we use a chain rule from this section, however, we can find a nice simple formula for doing this. We have the derivative of y with respect to x as the negative, the partial derivative of the function with respect to x divided by the partial derivative of the function with respect to y. So if I look at my function, and I have to set it equal to 0 first, so I have x squared plus y, xy plus y squared minus 9 is equal to 0. And then my partial derivative of my function with respect to x is just going to be 2x plus y. My partial derivative of this function with respect to y is just going to be 2y. Oh, and I have the plus x. So this rule, dy dx, is going to be the negative of 2x plus y over 2y plus x. And you're like, but that wasn't exactly what we got. Well, let's go back and check. Starting way up here. Boom, 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 up here. It is what we got. Exactly what we got. Which is way easier. But we don't get to learn the implicit differentiation in this form, the easier way of doing it, until we've learned the partial derivatives. So even though, wow, if I only would have known that in Calculus 1, how much easier it is, we've got to get to this level of understanding before we can say, oh, by the way, we can make this easier. We can also do this for when we have our variables that are in terms of 3 variables, so x, y, and z. So x, y, and z, if I have the partial derivative of my function, we set the thing equal to 0, of my function with respect to x, and then my partial derivative of x with respect to x, and all of that. Then my end result is this. If I want to find the partial derivative of z with respect to x, it is a partial derivative, it is my function with respect to x divided by my function with respect to z. And if I want to do the partial derivative of z with respect to y, then it is going to be the, don't forget the negative, the function's derivative with respect to y divided by the function's derivative with respect to x. So gives us these formulas. If I want to find it, partial derivative of y with respect to x, we talked about that. Partial derivative of z with respect to x, partial derivative of z with respect to y. Look at that stuff, provided, of course, that my function itself, all of them do not equal 0. So I'm asked to find dz dx and dz dy, partial derivatives. Well, all I have to do here is do the partial derivatives of each one of them and make sure I have a negative on each one of them. So if I want to do the partial derivative of my function with respect to x, this is going to be 2x, and then the sine of 2y minus 5z, that's going to be considered a constant there. And then I have the x, so this is the place in which I see the x is like an angle. So it is going to be negative y, and then it'll be multiplied by the negative sine of 6xz, multiplied by that angle, which happens to be 6z. So this is going to be 2x, and then it's going to be the sine of, don't forget to put that in parentheses, the sine of 2y minus 5z plus the y times the sine of x. Oh, I probably should put that 6z first. Let me put that first. So 6yz, the sine of 6zx. And I also want to have the partial derivative of my function with respect to y. And so this will be a constant now. Erase that. Now let me do this in blue. This will be the constant now, and this is the location of my angle, so I'm doing the derivative of sine. So the x squared is a constant coming along for the ride. The derivative of sine is cosine. And then I have my angle, which is 2y minus 5z. And then the derivative of my angle is just 2 because the 5z is a constant. And then I have minus. And so for this, the only thing that's happening here is this, and this is all considered a constant. And so the derivative of y is just 1, so this is going to be minus the cosine of 6zx. Now, I also need my partial derivative of my function with respect to z, because notice I have to divide both of these by my partial derivative with respect to z. And when I do that, and I look to see, okay, well, now as I look at this, the part that is the constant is going to be this part, because this is where my angle is. So the derivative of sine is going to be cosine, so it's going to be x squared, the cosine of 2y minus 5z. And then I'm going to multiply it by my angle, which happens to be the 2y minus 5z, and 2y is considered a constant, so it's just negative 5. And then I have minus, my y is going to be considered a constant, so that's coming along for the ride. The angle is where I see my z, so that I'm going to do the derivative of cosine, which is going to be negative sine of 6xz, and then multiplied by the derivative of that angle, which is just 6x. So, final answer. My partial derivative of z with respect to x is my partial derivative of my function with respect to x, which was 2x, the sine of 2y minus 5z, plus 6yz, the sine of 6xz, divided by, and there should be a negative out front, so let me put the negative there, divided by negative 5x squared, the cosine of 2y minus 5z, and then plus 6yx, the sine of 6xz. So that's that answer. And then my partial derivative of z with respect to y is a partial derivative of the function with respect to y, which was, and I'll pull the negative out front again, so minus, because it has to be a negative, 2x squared cosine of 2y minus 5z minus the cosine of 6xz in that parenthesis all over the same thing as I had before, so minus 5x squared, the cosine of 2y minus 5z plus 6xy, the sine of 6xz. So those are my two answers. Let's do this again for the next problem. And that's it. So really the hardest thing about this is keeping track of everything. So the first thing I'm going to do is find my partial derivative of my function with respect to x. This is going to be 2x. This is a constant. And then it'll be plus the cosine, because I'm taking the derivative of the sine, xy plus z. And the derivative of this angle with respect to x is just y. My partial derivative of my function with respect to y. Now, my x squared is considered a constant, so that's going to just not be of any concern, so it'll be 2y. And then here's my angle, so it'll be plus the cosine of my angle, xy plus z. And of course, the z is a constant, so it's just going to be multiplied by x. And then my last piece I have to find is my partial derivative with respect to z. So now we do it with respect to z. This is a constant, this is a constant, this is the angle, so it'll just be the cosine of my angle. And within my angle, those are considered constants, so it's just going to be multiplied by 1. So, now my derivatives, nice, easy peasy, lemon squeezy. My dz dx is going to be a negative 2x plus the cosine of xy plus z. Oh, I probably should put that y in front so I don't lose it. So y, the cosine of xy plus z, divided by the cosine of xy plus z. Could I distribute that? Sure. Am I going to? Nope. And then my partial derivative of z with respect to y is going to be negative 2y plus the cosine, don't forget that x, xy plus z, divided by the cosine of xy plus z. And those, bam, and boom shakalaka are my answers. And that's it.